Oh. I'm going to let's 21. No, no. Test 1, 2, 3. Yes. Okay. Okay, all right. I just saw, I just see someone right in this in the YouTube channel, right? Okay, okay, hereกิติพันธ์รัฐพัฒน์วีรพัฒน์พงพลประธานินเมธาสิทธิ์ปัญญา and Garcidilapit Dinapat Pisut. All right, I think I would misunderstand that today the lecture is going to be held at our school, but it's not, right? It should be still in the online manner, right? Okay. Sorry for that. I asked someone. Okay. Now we arrive at the almost at the end of this chapter. In yes, we're gonna see something happen, right? We wait for the water to okay, we have got already the pressure at the absolute pressure at the second floor, right? In the toilet here. I hope that you could hear me. Let me check whether anybody wanna join us in Zoom. No. Okay. Yes. Let me just the voice here. Okay. Yes, we know P2, and the last question to this problem is that how much time do we need to wait for filling 100 liter bottle? Okay, we wanna fill in the water into a bathtub. Okay, the place where you can lay your body down. And yeah, in one thing you need to know is that you have to convert, right, one liter, okay, to that is 100 times 10 raised to 3 cubic centimeter, right? And if you want to convert it to square meter, cubic meter, right? You would need to divide by 1,000, right? And finally, it's actually one. Oh no, it should be -6. Yeah. Okay, -6. Could you see it well? Yeah. Let me check the channel of the camera. Okay. Yes, and this one is 10 raised to -3 cubic meter. Okay, in the standard SI form. Yes, we have to prepare everything, right? And as you know from the continuity equation, the fluid speed is 8 meters per second at the second floor, right? Yes, and okay, we're gonna continue here. And as you know from the continuity equation, delta V continuity equation again. Okay, continuity equation. Oh, I forget to say some word. Well, good afternoon, everyone. Welcome you to SCI33206, which is physics number 5 อยู่ใน YouTube ครับ โอเคเห็นแล้วครับ yes, and yeah, this is a section for M604. We are almost at the end of this chapter. Okay, I hope you can see it well. This person supposing now has touched his name. Oh, sorry. And yes, you know that from continuity equation you have the in the first form, right? The fluid flow rate in terms of volume, delta V by delta T equals A and velocity, right? And because we actually, it doesn't matter whether you were going to use the flow rate at the lower floor or in the upper floor, okay, because that would be the same. Okay, and where is the house? Okay, here. Okay, whether you use the A1 V1 or A2 V2 here, you will get the same value, the same product here, which is the fluid flow rate in terms of volume. All right. Yes. Let's say we use the values at the second floor. Okay, we wanna wait for water to be filled in container, big container, which is called bathtub. Right? In here, as we know, we need the product of A and B, right? And the question is, let's say A2. The question is, they want to know how long we should wait, right? We should wait for the water, so it's delta T. So delta T will be delta V by A2 V2, right? Please note that the upper V is the volume and the lower V is the speed, right? The speed of water flow. All right, and yes, let's go ahead with that. Water flow rate. Okay, delta V is 100 liter, right? And it's actually 100 times 10 to the negative 3 cubic meter, or formally it's only 0.1, right? 0.1 cubic meter. It's not big, right? It's not a big amount of the water. And the second variable is A2. Okay, the cross-sectional area of the pipe in the upper floor here. Okay, of course, you know, it's the cross-sectional area of the pipe is circle, so it's going to be pi r2 square, right? R2 is the radius of the pipe in the upper floor. In this second floor, we have 1 centimeter diameter, right? So R2 is 1/2 of 1 centimeter, right? It's actually 0.5, right? Okay, times 10 raised to negative 2 in the standard meter, right, for the SI system. And we will substitute this into A2. It's going to be pi and 0.5 times 10 raised to negative 2 square. Okay, and the unit for it is square meter. Okay, everything in the SI scale. The next one is the speed, right? Speed at the second floor, and that's what the value we have got before last week, 8 meters per second. Okay, V2 is 8 meter per second. And now you substitute 3 quantities, delta V 0.1, okay, to this position. you substitute the cross-sectional area pi r2 square to this location. Okay, in the last variable, the third one is the speed. You leave it here. You get the time you have to wait for the water to be full in that bathtub. All right. So, oh, what happened? I didn't do anything. Okay. มือผมไปโดนปุ่มอย่างนั้น Okay. Yes, delta t from this expression will be delta v 0.1 cubic meter divided by A2, which is pi n 1/2 or 0.5 times -2 n square. And here is square meter, right? And the last quantity is the speed, right? Speed is 8 meter per second, right? And you can see that if you write the units appropriately, you could see the meter squared times meter will be a cubic meter, and cubic meter will cancel each other in the numerator and in the denominator lower here. And the second will be appear here. Okay, will appear here. What happened? We appear here at the numerator is going to be the unit of the whole thing here, which is second, right? Okay, let's substitute everything into calculator, and we're going to see what happened. Where is the Madonna? Oh, I'm stupid. Here. Madonna. And we used this one, right? 0.1 divided by pi. Okay, pi star 2 times the parentheses and square, right? That's the radius. Radius is 0.5 e minus 2. Okay, it's in centimeter. And the last one is the velocity, which is 8. Okay, 8 here. And we get delta t. Okay, delta t. It's 159. It's approximation. 159.15 second. All right. I hope it's correct. It's only approximation. We should not express it in good, in perfect way. Okay, it's 159 second, or if you want to see it in minutes, right? In terms of minutes, you may have to divide the whole thing by 60 seconds. You get 2.6526. It's approximation again. 526, right? It's somehow this in minutes. Okay, minutes would be more considerable. Okay, you have to wait somehow around 2.5 minutes. Okay, and then the water will be full in the bathtub. All right, and we complete this example, this scenario. If you have any question, just let me know. All right. And then we go to the we go to the last problem, which is about story of the airplane. Okay, here you consider the side view of the wing of the airplane. Okay, and we draw only the wing of the airplane. Okay, we don't draw the whole body of the aircraft. All right, and let the airplane moves from left to right, and when they move from left to right, it means like the air is moving from right to left, okay, in the opposite direction. And once we have decided the wing like here, okay, this is almost a straight line, okay, and this is the curved line, right? The curvy line. It's not a straight line because both air should reach the end at the same time, because they have the same, they are homogeneous, right? And yeah, once we decide the airplane to have the curve like this, it means that the speed of the air here in the upper portion of the wing should be faster than the air flowing under the wing, okay, because we have made this part of the wing to be almost as the linear as the line, right? So this one is curvy, it has more distance, okay, so the speed of the wind here should be larger. And with this property, if you apply the Bernoulli's equation, okay, let's say the pressure here and here are the same, right? Or if you get back to the Venturi effect, okay, it's like when you have higher speed, it means that you have lower pressure, okay. When you have you have lower speed, you have higher pressure, okay. When you have higher pressure here, okay, the pressure under the wing is higher than the pressure above the wing. So if you multiply the pressure by the area of the wing, you will get a force like this, okay, the force of the lift, the straight up force here, okay. This is the lift force caused by this phenomenon. But in nature, you have also the friction caused by the air, and that's called the drag force. And if you combine both the drag force and the lift force, you're gonna get the single vector, which is vector F here. And yeah, vector F is the total force exerted on the wing, okay. It's not right upward, straight up here, okay. It's a little bit deviated from the upward direction or upward vector here, okay. But the important thing is that you should have you should know, okay, how large is this area under the wing, okay. And this is William Wright or something, right, which invents the airplane and so on. Yeah, and yeah, he just applied the Bernoulli's equation. If you don't completely understand, let's get to an example. An airplane has wings, okay. So there are two wings, okay, on the right side and on the left side of the airplane, okay. In yes, when we have two wings like this, we cannot have only a single wing, okay. The aircraft is not going to be stable, okay. We have to use the two wings, okay. You know, in some airplanes they even use four wings or something like that, okay. The airplane has wings and each with area 4 square meter. Okay, it's not much, not a big amount. This wing is designed so that the airflow over the top of the wing will be 245 meters per second, and the underneath the wing, we have the speed of the air as 222. Okay, it's lower, as I told you. The speed of the wind here is lower than the speed of the wind above the aircraft wing, and find the mass of the airplane such that the lift on the airplane will support its weight. Okay, the lift on the airplane will support its weight. Okay, there is only a single force exerted on the airplane, which is the lift force, and there is another force which is the weight, okay, of this airplane. Assuming the force from pressure difference across the wing is directed straight upward. Okay, we don't pay attention to the drag force. Okay, let's say the drag force is 0. Once the drag force is 0, this vector F is gonna lie at the same straight upward direction to this vector. Okay, this one and this vector are the same. Okay, find the mass of the airplane. Okay, before we open and before we find the force, you know that we have to use the Bernoulli's equation, right? Bernoulli's equation. Okay, Bernoulli's equation says P1 plus rho G Y1 plus 1/2 rho V square, right? V1 state 1 and equals P2 plus rho G Y2 plus 1/2 rho V2 square. All right, rho V2 square. And assume that the pressure difference between P1, which is the absolute pressure caused by the air at the upper part of the wing, above the wing, and underneath the wing are the same. We assume that P1 is approximately the same as P2. Okay, and if the wing is thin enough, we would say Y1 and Y2 are almost or nearly the same. So this term could be also cancelled, right? Yes. No. We could not say P1 equal P2. I'm stupid. No. The pressure is not the same. I'm sorry for that. The pressure should be different. Okay. In this figure, pressure will be different. And then, because you know, usually P1 is greater than P2, right? Because here we have lower speed, and here the speed is converted to pressure. So so that the equality remains the same. We consider P1 minus P2. Okay, this term, and Y1, Y2. Y1 is approximately as Y2. Okay, when the depth the thickness of this wing. The thickness of this wing is not large. Okay, it's like few centimeters. Okay, we can neglect the potential energy and then now we are going to have on the left hand side P1 minus P2. Okay, and we move this term to the left, to the right hand side. Okay, then we have 1/2 rho V2 square open and V1 square like that. Okay, and yes, we just substitute the value of the each speed, right? But anyway, this is P1 minus P2. Let's talk about the lifting force. Lifting force, if this is the wing, if this is the wing, and here we have an area of this of the underneath the wing. Yes, lifting force here, F lift. Okay, F lift. F lift will be, as you know, P is F by A, right? From the definition of the pressure, you have P equal to F by A, but we want to find F. FL will be pressure V1 minus P2 times the area. Okay, the area, which is the underneath area of the this airplane. And yes, you know that P1 minus P2 is this one from the Bentley equation. You would get 1/2 rho V2 square minus V1 and times A. Okay, now let's open a new page. FL is 1/2, okay, and rho is the density of that fluid. So what is the density of that fluid? What kind of fluid we are talking about here? It's the air, right? The P air is 1.29. Okay, it's very light. P of the fluid, which is air, is 1.29 kilogram per cubic meter. We're going to use this 1.29 kilogram per cubic meter, and we have V2, right, which is speed. Above the wing, 245 meter per second, 245 square minus 222, right? 222, 3 times of 2 in oh, sorry for that. Square only, not triple. Okay, now it's time to leave these results into the calculator. We're gonna talk about the calculator. Here. Yes. That's the first quantity. Let's talk about FL, which is the lifting force. The lifting force is 1/2, right? 1/2 times the 1.29 times 245 square, 245 square minus 222 square. All right, and you get the the result. Okay, FL is 69. Right. Oh, sorry. FL is this value, which is 6, approximately 69 to 7.9. It's in Newton, right? But if you take a look at the airplane, okay, this is the airplane. I may not have a good drawing for that. And here is the wing, right? Wing of the airplane, and there is, oh, what happened? Cool. ครับอาจารย์ครับครับคุณครูครับครับเรียนออนไลน์ใช่ไหมครับอ้าวเหรอครับก็เขาก็พิมพ์เข้ามาพิมพ์ในซูมใน YouTube เหมือนเดิมครับคือใช่ครับคือผมเข้าใจผิดเหมือนดร.โชคสรันบอกว่าประกาศให้เป็นที่โรงเรียนแต่ว่าปฏิบัติจริงม.6 ให้เป็นออนไลน์หรือว่าเป็นที่โรงเรียนจริงๆออนไซต์ผมก็ไม่เข้าใจพูดกลับไปกลับมาหลายรอบก็งงอ้าวเหรอครับก็คือวันนี้ต้องไปใช่ไหมเดี๋ยววันศุกร์ผมจะได้ไปครับอ้าววันศุกร์เขาหยุดกันใช่ไหมครับผมไม่รู้เรื่องอ๋อตรงกับวันหยุดพอดีอ้าวอย่างนี้เป็นไงครับคุณครูอันครับจะเป็นอะไรไหมห้อง5อะไรอย่างเงี้ยครับอ๋อครับเดี๋ยวครับอ๋อโอเคครับได้ครับอยู่ในซูมอยู่ใน YouTube กันครับโอเคครับครับขอบคุณครับ alright my god okay oh yes alright yes let's continue our story. I misunderstood that we are still in the online manner. Otherwise, I'm gonna go to the school as according to the policy of the school. Okay, let's continue our sorry. You have the airplane here, and this is the lifting force. Okay, of lifting force of one wing, right? But if you look at the airplane, this is the airplane, right? And here you have 2 wings, right? The lifting force will take place at both sides of the airplane, okay, in both wings. So if you draw the body free body diagram of this system, you're gonna have the weight, right? The weights of the airplane, but on another side of the airplane, you have also another FL, right? So from the first law by Newton, you're gonna have sigma F, right? It's in a static condition, right? Static condition. And you're gonna have 2F, right? Okay, let's say going up is plus, it's positive. Okay, so 2FL and minus W will be equal to 0. And the question is the weight of the airplane. So W is going to be 2 times 2FL, right? And yes, if you substitute that one, it will be 2 and 6927.9 will be yeah, that's amounts, I don't know. Okay, and yes, W will be 2 times FL, right? And yeah, you get 13. Okay, 2 times of these values, 13, 8, 5, 6, blah, 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 Newton. Okay, and that's the answer to this question. Okay, and so the weight of the airplane, the mass, right? The mass 5655. Oh, what happened? We have to divide this value by my God, the area is just like that. Oh, no, it's empty. Yes, A delta P. A. Yeah, it's already two twice. Okay, and A and delta P in you have to divide this amount by 9.8. Okay, 9.8, and I don't understand why we could not get the same thing. 1.29, right? 1.29. 1.29. We have to multiply it with the area. Okay, my God, I forget the area. Okay, the area is 4 square meter. Yeah, okay, number 4, 2. And yes, F has to be recalculated because we forget 4, right? And the mass M will be W, the weight by G, which is let's say 9.8. Okay, we get this value. Okay, the weight will be, let's say F first. Okay, the force is not this one. The force will be 2.7712 times 10 to 4, and the weight, right? Okay, let's remove this one. Oh no. The weight, right, will be 2FL, right? And 2FL will be 2 times that value, 2.7712 times 10 is to 4, right? And yes, you're gonna get 5.5424 times 10 to 4, okay, in Newton, and you can convert it to the mass, right, by W equal mg, and m is going to be the weight, right, divided by g, and you just divide 5.424 times 10 to 4 by 9.8. You get the mass, which is 5.5 and 0.5 kilogram. Okay, so it's reasonable, right? A small airplane would have the mass like 5 tons. Okay, 5 5,000 kilogram, 5.5 ton. Okay, it's 5.5 ton, and nobody is in the YouTube at all. Only 2 people in Zoom, Hong and Shavin. Okay, Subasin, I think. สุภสินช่วยทำกันบ้านเขียนหนังสือตัวใหญ่ๆหน่อยนะครับalright
ได้ครับขอโทษครับ
เชิญครับ
เปล่าครับผมสุภสินเองครับก็เลยจะบอกว่าขอโทษที่เขียนตัวเล็กครับผม
อ๋อครับผมเจอมาหลายรอบครับการบ้านคุณตัวเลขนะครับมันดูยากครับมันก็พอดูได้หรอกผมเดาเอาครับโอเคไหม
เดี๋ยวครั้งหน้าเขียนตัวเล็กให้ครับตัวใหญ่ให้ครับขอบคุณครับ
โอเคwe have completed these we have finished this question and this example so it's time to say that we finished the first chapter which is about what is that which is about fluid and solid. All right, we have completed this chapter, solid and fluid. The next chapter is this one. Okay, it's the new chapter which is about atomic physics. Okay, it's an advanced story. Okay, about atomic model and other topics like quantum theory, okay, quantum physics, and so on, right? We may even touch the story about elementary particle or standard particle, okay, which is a new topic, which is not finished in the real in the current state of the research. Okay, this is the second chapter for this semester. Actually, we have also another chapter, okay, after this one, after this chapter, which is called nuclear physics or something like that. If we have time, we would read that chapter. Okay, in this chapter, we have 3 topics. Okay, atomic models. Okay, we say models because there are several models the physicists have proposed or invented before. Okay, so there are several models. Okay, but most high school physics textbooks would pick up only 2 or 3 models, okay, for the assumption, for the background in atomic models. Okay, the actual model of the atom is very complicated and it would be skipped or beyond the scope of the high school physics. So yeah, we will talk about Rutherford model and Bohr model, right? Neil Bohr in not modern, okay, in the middle generation of the physics. We have wave particle duality, okay, which is presented, which was presented by Louis de Broglie, okay, a French physicist. In the current state of physics is quantum mechanics, right? And it has already the application in real world. Okay, it's quantum computer or quantum computing or something like that. Okay, the reference of this chapter could be found from the textbook number 1, textbook number 2, and textbook number 3. Okay, 2 major textbooks for us. Okay, let's start this chapter by introducing or by getting used to the word atom, how this word emerged, okay, in the history. The word atom is derived from the Greek words, okay, the Greek words which is called atomos, okay, atomos, meaning anything that is indivisible, okay, you know, division, right? Division, divisible means it could be divided, but indivisible means something that could not be divided. Okay, something that could not be separated in a tinier component. Okay, and at least 500 before Christian era, when the Greek philosopher whose name is Leucippus, okay, Leucippus, and his student, his pupil, Democritus, this teacher and student have put forward the notion that matter consists of invisibly small, indivisible particles, which they call atoms. Okay, and that's the origination of the word atom. Okay, from the Greek era. Okay, and you know, many stuff, okay, at the beginning came from the Greek era, right? So it's like Archimedes and so on, right? Yeah. By the beginning of the 19th century, John Dalton, okay, John Dalton is an English chemist. Okay, he's not physicist also at all. He worked on stoichiometry, and he suggested that each chemical element consists of its own unique kind of atom. Okay, so any matter should have its own unique kind of atom, and that's the belief by John Dalton in 1896. In 1896, a French physicist whose name is Henri Becquerel, okay, Henry Becquerel, but it's in the French way. I don't know. I have never studied French. Henri Becquerel, okay. He has discovered something which is called radioactivity. Okay, the radio wave, okay, generated by spatial element, okay, but it's dangerous. Okay, and 1 year later, Thomson, okay, J.J. Thomson, who is British, I think he is a British physicist, had demonstrated the existence of tiny particles, okay, much smaller in mass than hydrogen. Okay, everybody knew at that time that hydrogen is the smallest atom, but Thomson has had discovered a tinier particle than the atom by hydrogen. Okay, and yeah, hydrogen is the lightest atom, the smallest atom, and he's discovered the first subatomic particle, and it is known at that time as the electron. Okay, electron is still known, well known. Okay, is the stuff widely spoken nowadays. Okay, and it's still captured as one basic standard element. Okay, in the standard table. He also measured the charge per mass of electron. Okay, but he didn't know what charge of electron is. Okay, he could know only the ratio between the charge and the mass. Okay, which is quite surprising. Okay, that's the first progress in atomic model. Okay, because Thomson has discovered the electron already. Okay, in at least how many years? Today is 2021, right? 2021 is for 20, right? For 221 years, 24 years later. Okay, 224 years before. Okay, Thomson had discovered electron and and the charge per mass. Okay, in 6 years later, Ernest Rutherford and his student, I think Frederick Soddy, working at the McGill University in Montreal in Canada, found that actually Rutherford has worked before with Thomson, and he found that radioactivity occurs when atoms of one type transmute into those of another kind. Okay, you know that atom consists of proton and neutron, right? When the neutron number of neutrons is different, we have another form of electron of that element, but it's still the same element. Okay, and that's the result discovered by Ernest Rutherford and his student Frederick Soddy. And 7 years later, Millikan has extended the work by Thomson to find the actual value of the charge of electron. Okay, he made the first experiment to capture the value of electron charge, okay, by putting some charge onto the, I don't know, the vapor of oil or something like that. Okay, and then he could find, he used the result by Thomson, and he could get the actual value of the charge of the electron. Okay, in this topic, we are talking about something very, very, very small. Okay, very, very tiny. It's quite hard to imagine. Okay, we didn't talk about solid and fluid at all. Okay, you can imagine what's going on with solid and fluid flow easily, right? But this one in this chapter is what we cannot easily see by eyes. Okay, because the size is very, very small. It was known that the overall size of the atom is on the order of 10 to -10, right? Yeah, it's in the angstrom scale, right? Angstrom meter. And yes, let me capture something. Okay, all atoms except hydrogen contain more than one electron. That's the basic knowledge what they have found at that time. Okay, and if you take a look to the detail of the size of atom, for the gold, okay, the gold has the diameter of its atom as 1.44, okay, angstrom, 10 less to -10, okay, 10 to -10. For iron it has a smaller atom than a gold, okay, and it's only 1.26 angstrom. Copper is a little bit smaller, a little bit bigger than iron, but still smaller than gold. It's 1.28 angstrom. And then in table 1 นะครับวันนี้ผมต้องขออภัยด้วยนะครับสำหรับคนที่อยู่ซูมนะครับเพราะว่าผมนึกว่าให้ออนไลน์นะครับเพราะว่าเหมือนว่าดร. First ดร. ชกสลันเขาบอกว่าประกาศไปอย่างนั้นครับแต่ว่าสำหรับม.ปลายก็ยังให้เป็นเขาเรียกว่าอะไรให้เป็นออนไซต์ผมก็นึกว่าเป็นอย่างนั้นแต่เขาก็พูดกันในไลน์กลุ่มผมไม่มั่นใจว่าสรุปออนไลน์หรือออนไซต์นะครับผมก็เลยไม่ได้ไปนะครับถ้ารู้ว่าออนไซต์จริงๆผมก็ขับรถไปแล้วนะครับเตรียมไปหาคุณแล้วนะครับโอเค and yes example of metal atoms, right? Yeah, these are 3 examples of metal atoms. In table 1, diameters are slightly different, but they are all on the scale 10 to -10, right? And the size of this atom is said to have the order of magnitude 10 to -10. What's still missing at the time was how the positive charge and electrons are distributed within atoms. So it's like, you know that in that sphere, okay, of course we would imagine that the atom should have the spherical shape, right? Yeah, in that sphere, how the positive and the negative charges staying together, okay, in that sphere. That was still a question at that time, okay. And Thomson, during his life here, 1956 to 1856 to 1940, suggests the model of the atom, okay. And he suggests that, okay, because human tries to capture the nature, okay, human tries to understand what's going on with the nature. So Thomson was a pioneer at that time. He suggests a model of the atom as the volume of positive charge on the order of 10⁻⁻10 in diameter, and with electrons embedded throughout the volume, much like the seeds in the watermelon. Okay, if you imagine, if you consider watermelon, if you shear, okay, you get the red part, right? And inside the watermelon, you have also the seed, okay, the seeds which are in black, right? Okay, and the black seed just distributed, okay, inside the watermelon, and the black seeds are somehow like electrons, okay, that are embedded in the watermelon. That's the belief by Thomson. And here is his figure, his picture. He got the position, okay, the rank sir, because he worked in United Kingdom, right? JJ stand for Joseph John, okay, Thomson, English physicist, okay. He was the person who discovered the electron, opening up the field of subatomic particle physics. And his extensive work is on the deflection of cathode rays in the electron sense of in the electric field. He received the Nobel Prize in Physics for his discovery of the electron. Okay, you know that there is an organization, okay, which is quite well known in the physics society, and that is the Nobel Prize. Okay, that's the prize for any physicist who has done something very good, okay, each year, which has a very big impact to the society. You could also obtain the Nobel Prize if you work in physics and you have discovered something which is very, very useful, very, very important in the field of physics. Okay, your work can have big impact to other people. You could also get the Nobel Prize. Okay, but for me, I cannot. Okay, I work in engineering field. Electrons are like the seed, okay, of the watermelon, and they are just distributed inside the sphere, okay, in the spherical volume. That's the idea by Thomson. And next one, you know, that's in the same generation, there is another person, Ernest Rutherford. Okay, Ernest Rutherford worked with his student Hans Geiger and Ernest. Okay, the same same name, the same first name, Ernest Marsden. Okay, this group has had to perform a critical experiment showing that Thomson model is not correct. Okay, the idea of electron distributed inside the spherical volume is not correct. Okay, because just take a look at the following result, okay, in figure 2 and figure 3. They make, okay, we still don't have the figure. Okay, here is the experiment set up by Marston and Geiger, and actually with Rutherford. Okay, because these are two students controlled or governed by Rutherford. Okay, they are the student by Rutherford, and they make the experiment. Yeah, is the alpha particle source. Okay, you can pick up any rare earth element, okay, that can produce the alpha particle, okay, or the proton actually, okay, and they just it's not proton, it's a positive charge, okay, positive charge that could be distributed from these elements, okay, from this object, and of course the source of alpha particle could distribute alpha in every way, but we make a closed area and we just drill the hole to only this way. Okay, we have two plates, okay, the lead screen, okay, the lead is used to block of to obstruct the alpha particle. Okay, we will allow only the alpha particle through this hole, okay, and of course in other direction the alpha will be blocked, okay, they could not go, but along these two holes they could go in the straight line. And here we have a thin piece of gold, okay, thin piece of gold. What is the reason why we need, well, they have the thin piece of gold? Because they want to observe the structure of the atom of the gold, okay. They use gold as the example of the elements, and one of the reasons is that the gold can be made very, very thin, right? You know that for the Buddhism, right, they use a small, very, very small piece of gold to attach to the body of the Buddha statue, right? Yeah, that's the reason. In yeah, the alpha particle is gonna be transmitted along this line, and yeah, once it hits the gold plate here, very thin gold, yeah, and they try to capture or be the behavior of the atom of the gold. Okay, what they could observe is that they could find the alpha particle in this way, and in other ways. Okay, especially behind the thin gold plate right here. Okay, yes, and you can see many layers behind the thin gold plate. And yes, once you make the experiment, okay, you have to try to write down the conclusion, right? Why something like this happened, okay? And the conclusion is the following. Okay, this is the explanation of all I have said. Okay, the experiment shown in figure 2 and figure 3, most of alpha particle passes through the foil as it were empty space, and a few particles were scattered through large angle. Okay, large angle. Atomic physics. These. Okay. Yes, many layers to place here behind the thin gold plate or the foil. Okay. Okay, it's better to use the word foil. Okay, you could realize that it's very thin. Okay, it seems like the atom is is hollow or something like that, right? Because we could see a large amount of penetrating layers of alpha, right? And a few particles were scattered through large angles. Okay, this is the scattering component. Okay, with large angle, it means the alpha particle may hit something, and that's why they get the deviation ray like this or like this. Okay, but most of them would be in this ray, so it means the atom should not be solid sphere like this, like what Thomson has suggested, right? I need to let you go at 14, right? We still have 10 minutes. All right. Yeah, that's the experiment by Geiger and Marston. And if you go further, there is a device which follows this name, okay, Geiger. And that's the figure by the book number 1, and the same experiments, okay, drawn by book number 2. You have the source of alpha particles, and you have a thin piece of lead. Okay, you drill a hole in the same way like this, and yeah, this is the closed area. This is the zinc sulfide, okay, screen, okay, to obstruct alpha. Otherwise, the alpha would get out of this area, and it could hurt something. Okay, alpha particle is not good for human cell or human body. All right. Yes. This is the explained by Cambridge University, and alpha particles used in Rutherford experiments. Okay, and what is the meaning of alpha particle? Alpha particle means the nuclei, okay, several nuclei of helium atoms. Okay, you just pick up helium, okay, and you throw away the electrons, okay, and that's why they get 2+ here. Okay, only the nuclei means the plural of the word nucleus. Okay, several nuclei of helium atoms. Okay, helium is a little bit bigger. The next element is bigger than hydrogen, right? The second element bigger than hydrogen. Okay, in figure 2 and figure 3, gold was used because it can be beaten into extremely thin sheets. Okay, and the case in which the alpha particle can pass through a thin metal foil shows that they must be able actually to penetrate into the interiors of atom. Okay, they just make the conclusion here, because this one is really thin, so you would imagine that the actual shape of the atom is not solid volume. Okay, it's not solid sphere. It should be hollow somehow, but which way should be hollow? Which type of hollowing should it be, right? And yeah, if you take a look at this part closely, you could see that the arrangement of several atoms of the girl, okay, are something like this. And of course, this is the layers of alpha particle in let's say we have a nuclei, okay, of the gold atoms, and they found that the nuclei should be very, very small, right? We know before that the atom is on the order of 10 to -10, right? But something at the center should be extremely small than the size of that atom, and it's going to be called nuclei. Okay, nuclei. A number of particles penetrate the foil or scatter to various angles, indicating that the gold nuclei are very small and contain nearly all of the gold atom mass. Okay, they realized that the whole mass of the core atom would be caused by the nucleus only. Okay, and yeah. Okay, now we pass to, okay, and in Thomson model, if it is the case, the alpha, when the alpha particle move, okay, through the solid volume of the model by of the atom, okay, modeled by Thomson, Rutherford calculated that the maximum diffraction angle of the alpha particle that could take place in this scenario is only a few degrees. Okay, if the Thomson model is correct, but it's not the case, as you can see here. Okay, it's not the case because you have a big amount of reflection angle, you have a big deviation, you have a large number of penetrating components, okay, behind the gold sheet, right? So the Thomson model is not correct, okay, because the experiment doesn't coincide with the prediction by mathematics here, okay. And yeah, if the Thomson model held true, positively charged alpha particle would never come close enough to a large positive charge to cause any large angle diffraction, okay. And yeah, because alpha particle comes with speed, right, and it doesn't hit anything, there should be only repelling force right here, and repelling force would cause the alpha particle to move in this way, right, a little bit deviate from the straight line. But it's not the case when you compare it to the experimental result. Yes, only interactions with the positive charge, which is tied to the most of the mass of the atom, okay, and the deflection angle here should take place or should have some result only the nucleus of this atom. And Rutherford explained this result by assuming the positive charge in an atom was concentrated in a region called the nucleus, and the nucleus was assumed to be small relative to the size of the atom, which is this one, okay. Nucleus is like a point, okay, here inside this circle, but it's not actually circle, it's in three-dimensional, it's a sphere, okay. Okay, Rutherford's experiments establish that the atom does have a nucleus, which is, so in conclusion, Rutherford's experiment comes up with the nucleus should be small, it should be very dense structure, and is no larger than 100 times the atom size, okay, which is the 10 to negative 12 meter, okay, in diameter. And the nucleus occupies only 1 by, I don't know, 10 to 12, 1 by 10 to 12 is only very, very small part, okay, 10 to negative 12 of the total volume of the atom. But it contains all the positive charge, okay, the positive just stay inside this, and at least 90.95 of the total mass of the atom, okay. So most of the mass of the atom is due to the nucleus, okay, and Rutherford suggested that perhaps the electrons revolve in orbits about the nucleus. They couldn't find with this experiment, we could not say how the electron are located. Okay, how the electron locates in the electron, but he tries to capture the behavior of the electron like this. Electron would resolve in orbits about the nucleus, and just as the planet revolve around the sun. Okay, in our solar system, right, we move around the sun, and it's like we are electron. Okay, on Earth, and our Earth is like electron. We move around the sun, and the sun is like the nucleus. Okay, they use the same idea as the solar system. Okay, and with the electrical attraction of the nucleus providing necessary centripetal force. Okay, you know that when you move around anything, you have the centripetal force, right? And because you have negative and positive charge, and there will be always the electric field, right, between those two kinds of charges, right? And that electric attractive force should be enough to compensate the centripetal force. And here is the result predicted by Rutherford, right? Thomson, sorry. And Rutherford just formed up another model of the atom like this. There should be positive charge, which is the nucleus, right? And the size of the whole atom is like this. Okay, and sometimes when the alpha particle hits the nucleus, you get a diffraction component or diffraction angle like this. Okay, and I think we need to stop right now, right? แต่ว่าห้องจริงมันไม่ต้องเบรกใช่ไหมครับใช่ไหมเอ่ยชวินกับสุภสินเดี๋ยวผมขออนุญาตแคปเจอร์หน้าจอก่อนนะครับเพื่อส่งให้คุณดูนะครับ Right, we don't need to have the break unlike the online manner, right? หรือว่าต้องการเบรกไม่เบรกแล้วกันเนาะ right ไปแบบเต็มเวลานะครับเพื่อว่าเนื้อหาเราจะได้ไปข้างหน้าต่อครับ Oh my god, just let me know. They have here this one. Okay, something like this. This one, right? Okay, that's the list of whole people, the whole list of people signing their names. Okay, ไปต่อนะครับ14-20นะเพราะว่าห้องจริงที่โรงเรียนมันไม่ต้องเบรกไปเต็มเวลาแล้วกันนะครับ Okay, yes, any electrons belonging to the atom were visualized as orbiting the nucleus, much as planets orbit the sun, as shown in figure 7. Okay, in figure 7 here, this is the model of Rutherford's system. Okay, we have the nucleus, okay, the heart of atom, and we have the orbits of the electron movement. Okay, the electron just move around the nucleus in a circular way like that. Okay, it's rotational way. Okay, and yeah, but this movement is proposed as in a plane. Okay, you know plane. It has only two-dimensional. Okay, two-dimension width and length, right? There is no height. Okay, and that's why it's called Rutherford planetary model of the atom. Okay, Anyway, two basic issues remain in Rutherford's planetary model. The first one is that the Rutherford model was unable to explain why an atom emits certain discrete characteristic frequency of electromagnetic radiation and no others, right? And yeah, you get only discrete frequency of electromagnetic wave, electromagnetic radiation from the atom, but you don't have continuous electromagnetic radiation. What is the reason behind that? Okay, because from the classical physics, when you have rotation of anything, this thing, the electron, it should give you some electromagnetic effect, right? But it's not continuous, right? So electron doesn't eventually spiral into the nucleus, or if they move or they rotate like this, they should lose their energy and they should finally reach the nucleus, like in the spiral way. But it's not the case. What is the reason behind it? And the Rutherford model cannot explain that. Okay, as it releases the energy all the time in terms of electromagnetic wave radiation, they release its energy in terms of EM wave, EM radiation, right? Electromagnetic, which is what you have learned before in the last semester, and caused by its centripetal acceleration. Okay, when the particle has acceleration, they should also radiate something, right? The electromagnetic wave in the circular movement. But Rutherford planetary model could not explain that. Yeah, that is still not perfect, right? So we move further. Yeah, here if you let light bulb, okay, it's like a lamp, something like that. And here is the lens. You just make a strip here, it's called slit, and the light that can pass through this slit is going to be in vertical direction. And you have here the next strip. It's another plate, the last plate. It's called diffraction grating. Okay, now the light has the diffraction here. It just go in this way. It goes in this way. Okay, and yes, once the lights get diffraction, it's gonna be decomposed. Okay, it's gonna be separated into different frequency. You can see here different colors from the same light. Okay, we start from the light bulb. Okay, we try to keep it in a certain way. We screen it and we let it go in a small bar so that there will be diffraction. And we want to see the components from the originating lights. Okay, they have several plates here. And this is the light bulb with heated filaments. Okay, this is the lamp with heated gas. Okay, with this, with another type of light source, we make the same thing. We have the lens to project where we control the intensity of the lights by using the lens here, and we block the unwanted lights, okay, by using the slit. There is a strip bar here, and we let the light pass through these plates, and it goes to this vertical bar. This vertical bar will decompose the light into several components, okay, into several frequency band. You could see the blue, the green, the yellow, the orange, and the red one, right? And the result here is that they are not continuous like this. Okay, this is the typical light source, right? It's the original lamp. If you have parsed the chapter of alternating current, okay, we are gonna have the lecture. We would have parsed the story by I forget his name. Who is that? Yeah, I forget his name. The person who invented the alternating current. Edison. Okay, Edison during the generation by Edison. Edison has built up the light lamp like this. Okay, and he sold it into the market, right? And that's a typical tungsten lamp, right? But for a special one, we just heat the gas. Okay, we just pick up the gas and let the gas stay inside this tube, and when we heat it by using cathode and anode or something like that to get strong electric field, and the energy by electric field will be transferred to the atom of the gas. Okay, and once the atom of the gas absorb the energy from the electric field, it's gonna generate the light, and this light is process, okay, is passed through several filters in the bar and so on, diffracting grating. And once there is diffraction, the single light is decomposed into different colors, different frequency bands. And what we could observe is the frequency bar of the light is discrete. It's not continuous. Okay, they just separate from each other clearly. Unlike this one, they are continuous. Okay, and yes, this is called a photoelectric effect. So what is the theory? What is the reason behind this? Okay, we at that time no one could deliver the proper reason. Okay, and this is what they could just make the experiment, but they couldn't find any reason to explain this phenomenon. Okay, what everybody once Rutherford proposed his model, everybody would suggest that according from the classical theory of physics, the object like electron should move in the spiral way. Okay, if you move like this, okay, it's gonna move in the spiral way because at that time it has acceleration like this. Okay, acceleration is not much. You get the light with this wavelength, and once you have more acceleration because you change your direction abruptly, okay, quickly, you get a shorter wavelength of the light. The color of the light should be also different. Okay, and here you change the direction so much, you get a shorter wavelength of the light, and here you change very, very quickly. So there should be the light that has very, very narrow wavelength. Okay, but it's not the case. Okay, if the Thomson model were true, it should be something like this. Okay, and finally, electron should be attached to the nucleus because electron has no more energy because its energy is released in terms of lights already. Okay, electron should spiral to the nucleus. Okay, if the Thomson model were true, emit continuous spectrum of electromagnetic radiation. Okay, at different location, it has light, right, and gradually lowers its energy. But it's not the case. From here, you can see the light you got is not continuous. Okay, the spectrum of the light is not continuous. it's discrete, okay, separate from each other clearly. So what should be the way to go further for physics at that time? So according to a classical electrodynamic theory, frequency of the transmitted electromagnetic wave should equal the frequency of revolution of the electrons around the nucleus or in their orbits, right? Because this is the theory which is well developed in the classical electrodynamic theory. Okay, and as the electron radiated its energy, the angular velocity would change continuously, and they would emit a continuous spectrum of the light. Okay, a spectrum means a mixture of all frequencies like this. Okay, we should get the continuous spectrum of the lights from these experiments if the Rutherford model is true. Okay, but it's not the case. We get discrete frequencies of the light. Okay, and not the light spectrum as actually observed here. This is the light spectrum. Okay, in a strip or in the bar wave. Okay, however, the Rutherford model of the atom gave away to that of Niels Bohr model. Okay, there was a physicist at that time, and his name is Niels Bohr. Okay, and Niels Bohr developed the model. Okay, from the idea by Rutherford. Okay, and which explain the characteristic radiation emitted from the atoms. Okay, Niels Bohr becomes a more complicated model than the model by Rutherford. Okay, so from what you have seen here, you can see the effort by human, right? They want to try to build up the model to explain the nature of the atom, right? From several experiments, from many kinds of experiments. Okay, okay, in conclusion, you could see that oh, I don't understand when this channel doesn't, it zoom, you could not see, right? Could you see? Yeah, but I have shared the screen already, right? From this one. I didn't share a screen. Okay, I didn't share it through screen, unfortunately. Okay, I hope that now you could see everything, right? Okay, let's draw some conclusion. Various phenomena like the electromagnetic radiation emitted by a heat object known as black body radiation, the emission of electrons by illuminated metals known as photoelectric effect, and the emission of sharp spectral lines by gas atom in an electric discharge tube, which is this one. Okay, which is this one. Okay, and yeah, these phenomena could not be explained by the classical physics. Okay, that's the problem. And in 1905, okay, Albert Einstein, okay, proposed the existence of discrete energy packets during the transmission of light. And yes, this model originates the so-called photon. Okay, photon is used to represent the light quantum. Okay, the packet of energy in the light. Okay, is a small energy packet of the electromagnetic radiation. And the relation of the energy is actually developed by Max Planck. Okay, energy is equal to a constant times the frequency. Okay, the frequency of the light. And this constant is dedicated to the person who discovered the constant, which is Max Planck, okay, a professor in Germany. And yeah, the value of this quantity is very, very tiny, 6.6, okay, blah, 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 10 to negative 34. And the unit for this is Joule second, okay. And F is the frequency in the standard way, in Hertz, right? Of the is the frequency of emitted photon. Okay, now the time is over. I need to quit the lecture for the section M604. Okay, let's stop it right now, and I think we should have, we don't need to have homework because it's going to be the replication as the result from last time, right? Okay, see you on next week, right? See you next week because Friday we are not going to have the lecture at all, right? Because that's the holiday. สวัสดีครับ604ครับบ๊ายบายครับ and โอเคครับผมนะครับถ้าคุณฟังอยู่นะครับก็คือผมลืมนะครับไม่ใช่ลืมหรอกเข้าใจผิดเองครับคิดว่ายังเป็นออนไลน์อยู่ครับก็M605 โอเคนะครับต้องขออภัยด้วยนะครับเห็นไลน์ตั้งแต่วันจันทร์แล้วแต่ว่าผมนึกว่าคำพูดของเขาเรียกว่าของดร.โชคสลันน่าจะเป็นอย่างนั้นอยู่มั้งอะไรอย่างเงี้ยครับก็คือเหมือนกับว่ายังให้ที่เป็นที่ออนไลน์อยู่นะผมก็เลยไม่ได้ขับรถไปนะแล้วเพิ่งพิมพ์ไลน์ตะกี้นะครับพอสอนไปแล้วเขาปรากฏว่าเขาให้เป็นออฟไลน์เป็นสอนที่โรงเรียนเนาะโอเคanyway good afternoon everybody welcome you to SCI33206 physics number 5 okay we are gonna have this lecture in online manner. Sorry for misunderstanding that the school is now open. Okay, the last problem for us in the first chapter is this one, right? It's the no. Okay, it's the environment about the aircraft wing, right? The aircraft wing แล้ววิงผลครับ and who else จะมีใครเข้ามาที่ซูมไหมครับโอเคไม่มีนะ okay yes I hope you could watch everything in theวันหลังคุณแจ้งผมก็ได้นะครับว่าเขาให้เป็นออนไซต์แล้วนะครับโอเคมีคนดูอยู่ที่ YouTube 1 คนนะเข้าใจว่าน่าจะเป็นลวิพลนะครับที่ YouTube นี้ไม่มี YouTube นี้ก็ไม่มีโอเคคุณอาจจะไม่ได้เตรียมอุปกรณ์กันไปนะครับไม่ว่าไงก็ตามโอเคthis is the wing of the aircraft. Okay, the aircraft moves from left to right. Okay, and yes, the wind is gonna point or take place in this direction. Okay, the wind is directed in this way, and we design the wing in a spatial manner so that it could lift or bring the wing up. Okay, when the wing of the airplane is going up, it will also take the aircraft body up. All right, and yes, when the wind touch the wing like this, okay, the wind touch the wing like this, you can see that this is the curve shape, right? The curve line, and of course there is also the part here, and when you compare the distance along these two traveling lines, this line is shorter than this line, right? This line is longer, okay, and yeah, because they start from the same air location, right? This in order to reach the same destination, the wind in this way should have higher speed, okay, and higher speed here, and you have lower speed here, okay, because you reach the destination at the same time as this one. So from the Bernoulli's equation, the difference to this movement is the pressure, right? The difference is the pressure. Okay, from Bernoulli's equation, you have P plus 1 by 2. Oh, sorry for that. It's rho gy, right? Rho g1 plus 1 by 2 rho v square, right? Assume that the thickness of the airplane here is not big amount. So the term potential energy here could be neglected. Okay, y1 and y2 are nearly the same. So the difference is the pressure at the lower underneath the wing and on top of the wing will be different. And the speed of the wind too, right? Above the wing, you have higher speed. Underneath the wing, you have lower speed for the wind. And yes, once you have lower speed, you would have higher pressure here, okay, under the wing. And with the higher pressure, if you multiply the area of the wing, you would get the force, right, which is from the definition F equal to P and A. All right, F is equal to P and A, and yes, you will get a force, and this one is the lift force. And once you let the airplane move, okay, because the air has the friction, right? Because air is a kind of fluid, and the fluid should have viscosity. The viscosity is actually the friction, and friction here is the friction here will take place in terms of drag force. Okay, there is the force, a tiny amount of force that try to obstruct the wing, obstruct the airplane to move. Okay, and this is the drag force. And the combination of the drag force and the lift force, you get the total force, which is vector F here. Okay, that's the actual force structure that take place in reality. Okay, yes. An airplane has wings, and now we arrive at one example at the end of this chapter, okay, which is a part of Bernoulli equation. Okay, an airplane has wings. Okay, of course, it's a plural form, so they have 2 wings, right? So let's draw the airplane like this, and you have the right wing, you have the left wing, right? And each wing has the area of 4 square meters, right? Airflow over the top of the wing in this figure is 245 meters per second here. Okay, the speed of the wind here is 245, and the speed under the wing it should be slower, right? The wind here should flow in the slower manner, so it has a speed only 222 meters per second. Okay, it's smaller than 245. Okay, find the mass of the airplane such that the lift on the plane will support its weight. Okay, and assuming the force from the pressure difference across the wing is directed straight upward. It means the lift force is straight upward, and the net force is also in the straight upward way. It means we neglect the drag force. Okay, we assume that we have only the lifting force here, and yes, we need to find the mass of the airplane here. Okay, this one. What is M of the airplane? นะครับทุกคนเข้าไปเช็คชื่อแล้วก็ไปเลยนะโอเคไหม Okay, anyway, let's go ahead with this with this phenomenon. Okay, we have the wing right here, wing shape like this, okay, and the speed here, right? Let's say this is V2, this is V1, right? And we have pressure P1, P2, okay, in the upper part of the wing. And from the Bernoulli's equation, okay, from the Bernoulli's equation, you have P1 plus rho G Y1 plus 1 by 2 rho V1 square equal P2 plus rho G Y, rho G Y2 and plus 1 by 2 rho V square, right? We assume that the height Y1 and the height Y2 are nearly the same, okay? Y1 approximately is approximate as Y2. So these terms could be cancelled, to each other, right? This term can cancel, could be cancelled to each other, and we have only two terms, right? And we want to observe, because this P1 is greater than P2, right? The lower, the underneath the wing, we have higher pressure, we have greater pressure, and we have lower pressure here above the wing. So we want to observe P1 minus P2, which is delta P. Okay, P1 minus P2, what is that? So if you move this term to the right hand side, sorry, there should be also a square here. 1 by 2 rho V1, sorry. Rho V1 minus 1 by 2 rho V2 square, you're gonna have 1 by 2 rho n V1 square minus V2 square, right? And that's it. Yeah, that's the delta P, the pressure difference. Okay, delta P, or the pressure difference. The pressure difference between under the location under the plane and the location above the plane. All right. And yes, now let's try to find the lift force. Okay, lift force here. Let's say if FL, okay, lift force is FL, and it's gonna be the product between the delta, the pressure difference in the area of the wing, right? Okay, if you have a bigger wing, you would have a bigger lifting force. Okay, it's linearly proportional to, right, because it's the multiplication factor. Okay, what else? You get delta P here and A here, and you could find FL, right? And if you take a look at the airplane, right, you have the airplane like this, and you have two wings. You have FL here on the left, and on the right you have, you should have also FL on the left, right? So if we take a look at the side view of this airplane, you have 2FL, right? The lifting force of both wings. Okay, and you have the weight, right, which is mg of this airplane. And the question is, what is the mass of this airplane? We are gonna say from the first Newton's law, sigma F equals 0. And let's say if going up is positive, we would have 2F2 minus W or mg, sorry, mg equals 0, right? And yes, this is F2. And yeah, we want to find M, right? We move mg to the right hand side and we move g to the left hand side. You're gonna have M equal to FL, right? To FL. To FL divided by G. Okay. And yes, of course, FL is the lifting force. It's the product between pressure difference and the cross-sectional area, right? It's 2 delta P and A divided by G. Okay. And from what we see before, delta P is 1/2 low and velocity 1 square minus velocity 2 square. So this one is 1/2, right? 2 and 1/2 rho V1 square minus V2 square. Okay, and that's the big parenthesis. And you have also here, you have division by G. You could see number 2 here could cancel each other, and you get constants like rho A by G times V1 square minus V2 square. Okay, that's the compact expression to this problem, right? If we go further, you would see that rho, what is the fluid? Rho air, right? Rho air. The density of the air, how many kilograms do we have for the air? Density of the air is 1.29. Okay, 1.29 kilogram per cubic meter. All right, rho air. And what else? Cross-sectional area. Cross-sectional area is 4 square meter, if I can remember properly. Yes, A is 4 and G, of course, is 9.8. V1 is the higher speed, which is 245, right? 245 meter per second. And V2 is the lower speed, which is 222 meter per second. Okay, and yes, the substitution to find the mass is the following. Mass will be rho is 1.29. Rho A is number 4 and divided by G, right, which is 9.8. And here V1 square. V1 square is 245 square minus 222 square, right? If you leave it into the calculator, if you leave this into calculator, you will get M equals 1.29 times 4 divided by 9.8 and times this one, right? 245 square minus, oh yeah, minus, not plus, 222 square, right, is going to be the result. What is that? Okay. Okay. Yes, the result is 6.9 279, right? 10 to 4, right? Kilogram. Yeah. It's like a กดถูกนะครับ 245 square 9.8 my god 9.8 so it's not a case, it's 5,655.5 kilogram, okay, approximation. So the mass of this airplane is around 5.5 tons, okay, 5.6 tons. Okay, you would know now how to solve this problem, right? When we have the problem about the airplane, when we calculate the lift force and the aircraft has 2 wings, right? We have to multiply the amount of lift force by 2, and we make it to be equal to the mass or the weight of this airplane, and we get the mass. All right. So it's time to say that we have completed the first chapter. Okay, everything is finished about the story of solid and liquid. If you have any questions, just let me know. If not, then we're gonna go further to the next chapter. It's M605 for you here. Okay, we will start today the second chapter for this semester. It's called atomic physics. Okay, atomic physics. It's totally different from the previous chapter. Okay, in the previous chapter we talk about solid and liquid, right? In yes, that's the stuff or the substance we can see by eyes, right? When the water flow or fluid flow or something. But in this chapter we will talk about something that cannot be seen easily by eyes. Okay, that could not be seen at all by eyes. You need to have spatial device or spatial experiment, okay, to let you realize what's going on with the phenomenon in related to this chapter. Okay, and the price for the spatial measurement is quite high. Okay, I don't think that any school would have that. Okay, and yeah, the content in this chapter is the following. We will talk about atomic models. Okay, you know that models has the plural form, right? Yeah, there are many forms for the atomic model, and we will talk only a major candidate for the atomic models, like J.J. Thomson model, Joseph James Thomson model, or the Rutherford model, or the Bohr model. Okay, but actually there are some more models apart from the Bohr's model. Okay, but those are the principal model that were chosen to be appropriate for you in the high school level. Okay, in the second topic, we will talk about wave particle duality. Okay, in some scenario, physics could not explain what's going on. Okay, when we are talking about something tiny, so there is an idea proposed by Louis de Broglie, okay, a French physicist, which says that wave, we know that the electromagnetic wave is not a particle, right? It's only electromagnetic wave, right? It has only electric field, magnetic field, okay, induced to each other all the time. But when we think that the electromagnetic wave has no particle at all, we could not explain some phenomenon, okay? But if we think that the electromagnetic wave or the EM can be have like the wave and the particle sometimes, yeah, with this way we could explain everything clearly, and that's why many people would believe the idea by Louis de Broglie, which is called wave particle duality. And we will talk about that later. And at the end of this chapter, we will go ahead to the so-called quantum mechanics. Okay, we don't talk so much about the advanced topic in quantum mechanics because it's beyond your level. We will talk about the state or how the electrons are located into electron orbits, okay, only. Okay, so quantum state will be the main target of this title. Okay, now let's start the atomic models, right? Okay, the word atom is derived from the Greek word which is called atomos. Okay, yeah, you know that many science and many stuff is derived from the Greek heritage, right? Because before the current generation, in the previous era, the Greek Empire was quite great, and they have big developments, and one of the development apart from the building is the science, okay, science or mathematics or something like that. And yes, some scientists at that generation in Greece proposed the word which is called atomos, and the meaning of this word is called something that is indivisible. Okay, indivisible. What does that mean? It means something that could not be divided, okay, or separated into something smaller. Okay, that's the smallest level. Okay, the meaning of atomos. Okay, at least 500 before Christian era, when before our 2021. Okay, so it means 2521 earlier, which should be the same generation as the Buddhism era or something like that. Okay, when the Greek philosopher, there was a Greek philosopher, his name is Leucippus, and his pupil Democritus. Okay, Democritus would be quite well known to you, right? They put forward the notion or the idea that talking about matter consists of invisibly small and indivisible particles, which they call atoms. All right, and yeah, that's the first generation, okay, about atoms. But there is no detail yet about the structure of the atom, right? Until 19th century, okay, this is the history, okay, which were recorded in the past. Okay, I don't know, maybe there would be some more information about atom, but this is only the available detail we could find on Earth, right? Maybe there was some developments before, but it was destroyed by time or something like that. Okay, but the one that was still recorded in for human is by the beginning of 19th century, and there was a chemist, and he is in England. He's English person, and his name is John Dalton. Maybe you have ever heard his name before, right? John Dalton. John Dalton worked in chemistry, and his specialized topic is stoichiometry. And in this area, in this work, he suggests that each chemical element consists of its own unique kind of atom. Okay, so each element should have its own atom. All right, in yeah, in 1896, the French physicist, his name is Henry, but I think it should be pronounced as Henri. Okay, Henri Becquerel. This guy still didn't discover the atom, but he found that the substance that is spatial can produce the electromagnetic wave in terms of light or any radiation. Okay, and that element is called radioactivity. Okay, it's not straightforward to the atomic model, but it could be seen as the development about atomic models. Okay, and 1 year later, from the continent in Europe, from the European continent, let's move to the channel, and to British, to Great Britain. There was a person whose name is Thomson. Okay, J.J. Thomson. J.J. stand for Joseph John. Okay, the same like here, John Dalton, but this one is Joseph John Thomson. Okay, this person has demonstrated the existence of tiny particles, and he found that these particles are smaller in mass than hydrogen. Okay, which is the lightest atom at that time. Okay, they know that from chemistry society or even physics society, they agree to each other that the smallest atom is hydrogen, which is also the lightest one. Okay, and he discovered several things about these tiny particles, and this is the first subatomic particle. Okay, and it is known as electron. Okay, yeah, electron was discovered in the history, and he could measure the one property of the electron. Okay, which is not explicit. Okay, it's only implicit quality, and that value is called charge to mass ratio. Okay, charge to mass ratio, which is E/m. Okay, you know that E is the electron charge, right? It's 1.6 times 10 to negative 19, right? And the mass of the electron is 9.1 times 10 to negative 31, right? Kilogram. Yeah, but the value of the electron charge and the mass of electron were still unknown at that time. Okay, it's 1897. How many years ago? It's 4 to in 2, right? 4, no, 224 years ago, okay? 224 years ago, J.J. Thomson has discovered the ratio of charge to mass, okay? Or maybe this year you could discover something, okay? Because this is the history about the discovery of atom, okay? Maybe because the knowledge doesn't stay constant, okay? It changes with time, okay? Even during my generation, the solar system include also the Pluto, but nowadays Pluto is not considered as a part of our solar system. Yeah, okay. Yeah, that's what we have to believe because they use some spatial property. Okay, in 1903, another person whose name is Annette Rutherford and his colleague Frederick Soddy, they both work at McGill University in Montreal. This university is a very, very good one. Okay, if you have a chance, you may go to this university, okay, to study. And they found that radioactivity occurs when atoms of one type transmute into those of another kind. You know that an atom consists of a proton and neutron, right? But the people at that time didn't know that, okay? But in general, right now, you know that atom has both proton and neutron. For the atom that has a different number of neutron, you still get the same element, but it's a new type of atom, okay? It's a similar type of atom to the original one. And yeah, if you change from the spatial type of that atom to the typical type of that atom, you change, or it's called transmute, okay, the atom, you get the radioactivity, okay, the radiation in terms of particle or electromagnetic wave. Okay, that's what the result discovered by Annette Rutherford and Frederick Soddy. In 1910, Millikan, this guy is quite clever. Okay, he used the result from the 13 years ago experiments, okay, by Thomson. Okay, the result by Thomson 13 years before his work, Millikan has completed the first measurement of electron charge, okay, which is nowadays known nowadays 1.6 times 10 to negative 19 coulomb, right? Yeah, the value of E now emerges, okay, emerged by the time, and it was known that the overall size of the atom is on the order of 10 to negative 10 meter, right? Or simply speaking, it's angstrom, right? This scale, this is angstrom, and all atoms except hydrogen contain more than one electron. Okay, every atom except for hydrogen has the number of electrons greater than 1. Okay, they have at least 2 electrons. Okay, yeah, let's get into the detailed example of metal atoms. For example, the gold, right? The gold has the diameter as 1.44 angstrom, right? 10 to negative 10. And iron has the diameter in terms of 1.26. Okay, the gold atom is bigger than the iron atom, right? In 1.26 10 to negative 10 meter, and copper here has a diameter as 1.28 times 10 to negative 10 meter. Okay, it's angstrom too, right? The same order. All right. Yeah, we you could see the metal have almost the same size in diameter to each other, right? In the 1.44, 1.26, 1.28. Okay. And yeah, in table 1, diameters are slightly different, but are about 10 to negative 10. The size of this atom is said to have an order of magnitude 10 to negative 10 or angstrom. Okay. What's still missing at the time was, of course, many people know that the atom should contain both positive and negative charges, right? But they didn't know how the positive charge locate or distribute, how the negative charge locate or stay in the atom. Okay, so the people believe that the atom should have the spherical shape, or should be in sphere, right? Because they measure the diameter. They try to measure the diameter of the atom, and yeah, Thomson has suggested a model of the atom as the volume of positive charge on the order of 10 to negative 10. Okay, spherical form of positive charge only. Okay, and with electrons embedded. Okay, now the negative charge come into play. The electrons are embedded throughout the volume, much like the seeds in a watermelon. If you take a look at the internal of the watermelon, right, you're gonna see something red, and at the same time you would see the seed, okay, right, the black seed or the brown seed of the watermelon inside the watermelon, right? Yeah. Here is Joseph John Thomson, right? He is English physicist in 1856. In 1940, Thomson usually considered is a great person. Okay? He is considered as an important person in the story about atomic models. Okay, because he has made a big contribution to that. Even his work is not completely correct. Okay, but anyway, he got the rank at that time as Sir. Okay, it's like Sir Alex Ferguson or something that the trainer of the famous football team, right? Yeah, what he suggests is the following: we have a solid volume, okay, also a solid form, a solid sphere, and you have tiny pieces, okay, several tiny pieces of the electron, okay, staying or embedded inside this sphere or in this watermelon. It's like you have the seeds of the watermelon inside the watermelon, okay, and yeah, the seed just stay constantly like that, right, inside the watermelon. Yeah, let's talk about the detail of this person. Thomson opened up the field of subatomic particle physics with his extensive work on the diffraction of cathode rays in an electric field. He received the Nobel Prize in Physics in 1906 due to the discovery of the electron, okay, because he discovered the electron. Is a great impact to physics, right? What he discovered has a big impact, not only to physics, to electrical engineering, to chemistry, to several branches, okay, in science, okay. And yeah, let's go further. You could see that the model created by him is not correct, right? It's not what we realize nowadays. Okay, yeah, the people try to make a good model about atom, okay, and yeah, the research was quite popular at that time about the model of atom. Okay, you just create any, you just imagine, okay, any type, any model of the atom. Okay, if the people believe in what you created in your head, okay, it will be widely spread. Okay, but in order to believe what you have created, there should be some reason behind it. Okay, it means that the model you create should explain several phenomena related to the atomic experiments. Okay, then your model is going to be widely accepted. But if your model, the model you created, has nothing to do with the phenomena, with the realistic phenomenon, it's not going to be widely accepted. Okay, it's going to be thrown away into the trash or in the bin, something like that. Okay, yes, in 1910, 1911, Ernest Rutherford and his student, okay, because he was the professor and he should have the students like PhD or doctoral degree students or something like that. And both of students are were known as Hans Geiger. Geiger is well known for special device in physics, right? Ernest Marsden, okay, these two students by Ernest Rutherford made the experiments, okay, critical experiment showing that Thomson model could not be correct. Okay, they would find if the model by Thomson is correct, the experiment should be like that, so on, right? But yeah, they make experiments and they try to infer to the model by Thomson, but it's not the case. Okay, what about his, or what about their measurement, the experiment? It's somehow this, okay, in figure 2 and figure 3. Okay, both figures represent the same thing. Okay, but this one is taken from book number 1, this one is taken from the book number 2. Okay, but they are exactly the same experiment that Geiger and Marsden have conducted, okay, have done. All right, let's get into the detail. What is that? Perform a critical experiment and in figure 2 and figure 3, most of, okay, here you see anyway anything start from left to right, but also here the experiment by Geiger and Marsden. Let's take a look from the left side. Here is the source, okay, and they were quite clever actually. They just take any isotope material, okay, and this isotope will deliver the alpha particle. Okay, let's talk about alpha particle. What is that? Okay, if you can remember, alpha particle is the nucleus of helium atoms, right? Which is helium-4 okay, helium-4 2 is the number of proton right here, and 4 is the number of protons plus neutron, right? So you have 2 neutrons, and 2 plus on the right side means you throw away electron from this atom. Okay, so you would have only unstable state of the atom. Okay, that's called alpha particle. Okay, it's a helium atom, but the helium atom without 2 electrons. Okay, helium actually has 2 electrons, but we consider the condition when helium atom doesn't have their own electrons, okay, doesn't have its own electron, and that's the positive ion. We could say also that, okay, alpha particles are chosen as the traveling elements, okay, to hit the atom. And ผมขออนุญาตเข้าห้องน้ำแป๊บนึงครับขออนุญาตเบรกเข้าห้องน้ำแป๊บนึงครับปัสสาวะ Okay, let me get back to the experiment by Marsden and Geiger. Okay, the students, graduate student by Professor Anders Rutherford. Okay, we start from the left side. We have a low activity element or material that could radiate the helium nuclei, right? Plural form of nucleus is nuclei, okay, which is this one. Okay, we have several nuclei and of the helium, okay, without electron at all. Okay, and this is because it's the light atom, right? Helium has 2 protons, 2 neutrons, right? So it could move easily, and it just move, right? Because this is the source. Okay, it has high energy. They just kick the helium nuclei out, and then helium nuclei sometimes are known as alpha particles. Okay, move in the straight line. Okay, they move in every direction actually. Okay, they just these sources radiate the alpha particle in any direction, but in order to get a good experiment, we will allow only a single ray of the alpha particle to pass through the hole of these plates. Okay, this is the hole okay, prepared before. Okay, this is the plate which is made by lead screen. It's made by lead. What is the reason why they use lead? Because lead could obstruct the penetration by the alpha particle. Okay, lead is a heavy enough element, okay, to block the unwanted amount of alpha particle. Okay, and yes, once we have prepared a hole here, okay, there is no obstruction at all, right? The alpha particle could go and pass through this hole. It go further in the straight line way, and when it passed the second hole, the other components are completely blocked. Okay, we have only a single line, and yes, of course, the alpha particle go further. In here, they prepare a thin piece of gold. Okay, this is denoted by yellow, and it's made of gold. Okay, or sometimes it's called gold foil. Okay, gold foil is located as the center of this circle area. This circle area is a screen of scintillation or zinc sulfide. Okay, zinc sulfide is made of zinc sulfide. The functionality of zinc sulfide is that we want to block the alpha to not go further, okay, to not be harmful, or we want to observe the points of the zinc sulfide when it hits, when the alpha hits the zinc sulfide, we could see how many points appear in that zinc sulfide, okay, and then we could see this is the number of rays and so on, right? When we have several points of hits here, okay. What is the reason why they use the gold as the target? Why don't we use other type of elements? Okay, why should we use gold? Any idea? Only a single person watching this live stream. Okay, why? Okay. Yes, the reason behind this selection is the following. You know that you can make of course, we want to observe the behavior of the atom, right? So that we could build up a good atomic model, right? So in order to observe the atom, we need any piece of metal, or not only metal, any kind of object that should be very, very thin, right? Extremely thin. And gold is one of the metal that could be prepared in a very, very thin form, right? Yeah, gold was chosen at that time. It's like you go to, if you are Buddhist, you go to the temple, there is an activity, right? The people lay down the gold foil onto the body of the Buddha statue, right? And that's the same way, okay? Because the gold can be made to be very, very thin. And that's why we could see very well the effect of the atom, right? Okay. Once the alpha ray hits the foil, the gold foil here, the result that Geiger and Marsden could observe is the following. They count down the number of points on the zinc sulfide plates, and they could see that the plate straight behind the gold foil has several points. Okay, you could observe several points in the zinc sulfide at this location. You could also observe a very, very small number of points here in the zinc sulfide in this location, zinc plate. Okay, and what else? The zinc sulfide is the indicator, right, to show you the number of points. Okay, in yeah, the result just emerged like that. And now let's get back to what could we think about that. Okay, what could we think about the atomic model when we have these experiments? Any idea about that? Yeah, they were quite clever in actually to observe the behavior of the atom. Okay. Okay, particles used in Rutherford experiment were later identified as nuclei of helium atoms. Okay, it's known as alpha particle. Gold was used because it can be beaten into extremely thin sheets, and alpha particle can pass through a thin metal foil, and it shows that they must be actually able to penetrate into the interiors of the atom. Okay, so because we have seen many points or many layers here, it means the atom of the gold should be should have empty space, right, or hollow or something like that, right? Yeah, that's the first information we could realize the actual property of the atom. Okay, that's why I say they are quite clever. Okay, if we cut the thin plate of the gold, okay, of course we cannot have only a single layer of the atom. This layer should be very thin, but there are still many atoms of the gold. Okay, the truth is that once that you are and particle pass through this thin layer of the gold, there are many empty spaces the alpha particle could go through this foil. But there are some cases, there are also few cases that alpha particle just hit something and it goes in a deviated direction like this, or even in the reflection direction like this. This is the deviation direction, this is the reflecting way. Okay, a number of particles penetrate the foil and scatter to various angles, indicating that the gold nuclei are very small and contain nearly all of the gold atom mass, right? Because once it hits, once the helium or alpha particle hits the nucleus, it can have a big deviation angle. They believe that these points should be very heavy. Okay, should hold a large amount of mass of the whole atom, right? So yeah, they just made the analysis like that. And if the atom follow from the Thomson suggestion, Thomson, Joseph John Thomson suggests that the atom contains positive charge, right, in the whole area, like here, right? And alpha particle is a positive charge, and when a positive charge moves with momentum with speed like this, of course, once it enters this area, plus positive charge and positive charge would have would result in pushing force, right? And that force will make the movement of the alpha particle in this way. Okay, they just change the direction of the alpha particle because there are some force acting on the alpha particle during this route. And out of the atom, the alpha particle just go again linear in a direct way, right? Like this, right? Okay. Rutherford calculate the maximum deflection angle by Thomson model. We should have only few degrees for the deviation if the model of the atom by Thomson is true, but it's not the case if you compare it to the actual result from the experiment. Okay, experiment will not deny you. Okay, will not give you some false. Okay, and Rutherford explained this result by assuming the positive charge in an atom was concentrated in a region called the nucleus. Okay, because when it hits that component, the alpha particle could go in a deviated direction like this, right? It can even have the reflection. Okay, so that mass, that portion should be heavy. Okay, should have so much mass in the whole atom. Okay, in the positive charge in an atom was concentrated in a region called the nucleus, and the nucleus should be small relative to the size of the atom. Okay, Rutherford's experiments therefore established that the atom does have a nucleus. Okay, like this, does have a nucleus like this. Okay, the point here at the center of the circle, but it's not actually simply two-dimensional circle. It's three-dimensional sphere. Okay, and very dense structure is no larger than 10 to negative 12 meter in diameter. Okay, it's not bigger than that. Okay, it should be smaller than 10 to negative 12. Okay, what is that? 1/100%. Okay, 1% of the whole size of the atom. Okay, the nucleus will possess only 1%. Okay, 1/100. Okay, assume that an atom is of the size 10 to negative 10 meter in diameter. The nucleus is only 1/100. Okay, size of that. So you could see that the nucleus would be very, very small, right? Comparing to the whole piece of atom. Okay, the nucleus occupy only 10 to negative 12 of the total volume of the atom too. Okay, in yeah, all the positive charge in at least 99.95 of the total mass of the atom. And yeah, it contains mainly the mass of the atom, 99.95. Rutherford suggests that perhaps the electron revolve in the orbits about the nucleus, just as the planets revolve around the sun. Okay, all right. With the electric attraction of the nucleus providing the necessary centripetal force. Okay, you know that when you have the rotation around the nucleus, there will be centripetal force, right? And what kind of centripetal force in this three? It should be the attractive force, okay, caused by the opposite polarities of the charges, right? Because electron is negative, there should be positive inside in the nucleus, and that's why they say electrical attraction of the nucleus. And here is what they assume. Okay, they imagine that the atom should have nucleus which is positive, and electron should be a tiny particle, right, around the nucleus. And once you let the alpha particle go, you see the reflection like this, because this alpha particle unfortunately hits the nucleus of that atom. Okay, and the nucleus of the atom is heavy. Okay, because it contains almost 100% of the mass of the atom. Okay, any electrons belonging to the atom were visualized as orbiting the nucleus, much as planets orbit the sun, as shown in figure 7 here. Okay, this is the idea suggested by Ernest Rutherford. He said that the atom should have nucleus, which is positive in terms of charge at the center, and there should be electron moving around the nucleus. The electron should move around the nucleus in either clockwise direction or counterclockwise direction, but this movement take place in a horizontal plane. Okay, it's normal plane, so it's not three-dimensional. Okay, this is what Rutherford suggests about the atomic model. Okay, and now anyway, the model by Rutherford has some problem, because if you use the knowledge by classical physics, Rutherford model could not explain why atom emits certain discrete characteristic frequency of electromagnetic radiation and no others. The electron doesn't eventually spiral into the nucleus. Why? Why not? Because when any object moves and it changes location, it changes its acceleration, they should release the energy. Okay, it's like you run and you want to increase your speed, you need to consume some energy, right? If you run with a high speed and you change your speed to be smaller, to be slower, so you would release the energy. Okay, it's same as here. Once even the speed remains the same, but there should be acceleration, because they change its direction all the time. Okay, they didn't go straight in a linear way like that. Okay, and yeah, as it releases the energy in terms of electromagnetic wave, they should spiral. Okay, they should have no more energy, and they should finally be attached to the nucleus, because this is the negative charge and here is the positive charge. Okay, once it's released the energy in terms of light, this one should get to the should be so close to the proton. Now let's consider the corneal spectrum caused by a hot light source, and discrete spectrum caused by heated gas. Okay, this is the light source. If you have ever seen the chapter 3, which is something about alternating currents. Okay, alternating currents. In that chapter, you would see Thomas Alva Edison, right? And Thomas Alva Edison was is the person who has made the light bulb. Okay, the first person, and he sold it on the market, and that's the light bulb, right? It's caused by let the current flowing into the coil and so on, right? When the coil is heat, it's we are gonna have the light source. Okay, and once we let the light source be concentrated on a certain direction, okay, we use the lens here, okay, to concentrate the rays of the light to a certain area. And we have next the plate, and this plate has the bar, okay, or strips, okay, empty space right here. You can drill, or you can use any kind of device to make a hole here. And of course, the light is going to pass through this vertical bar, and the vertical bar is going to pass another bar like here. This is another plate, the second plate. They have exactly the same location of the strips. Okay, this one is used to block all other components of the light. This one is used to make the light have some behavior which is called diffraction. Okay, to let the light have diffraction property, and of course the light will be decomposed into different frequency. Okay, and from this light source we get the continuous. You can see the transition of a color to another color is quite smooth, and that's called continuous spectrum light. But once we change the input source for the light, we use the lamp with heated gas. Okay, you just use any kind of gas like helium or any neon or any kind of elements. Okay, and you put the electric field inside. Okay, and you let the current flow to these nodes. Okay, there will be electric field. If you let the electric field be stronger, the air inside this tube is going to absorb the energy in the electric field. And once it's absorbed the energy, it will radiate the light to these three plates, okay, in the same way as these one. But unfortunately, with such type of heated gas, the outcome on the screen is the spectrum of the light, but they are quite well separated from each other. They are not continuous like this. So what is the reason behind that? Okay, so how could the Rutherford planetary model explain this behavior? Because it's really impossible, right? Okay, because what Rutherford suggests, the ratio or the speed of this particle should reduce, right? Because it changes its direction all the time, and when it changes acceleration, they should release the energy in terms of light. When anything that has no energy, it means, yeah, it should stop, right? Yeah, during this motion, the power spectrum should be continuous. Yeah, it's continuous in this way. But for this heated gas, we get the discrete spectrum of the lights. So what's going on? Okay, this is the figure that tries to realize the actual behavior of the Thomson atomic model. It has a large lambda, which is wavelength here, and when it changes the direction, okay, they will release all the time the lights. Okay, let's say it's magenta with long wavelength. Okay, and once it moves, it should move in the spiral way, and it has lower speed again, yeah, because it releases its own energy to be light, and yeah, they will produce also the light in a different color, but in shorter wavelength. And here they have more and more revolution per time, right? So when you have more revolution per time, the frequency of your light should be also higher, and that's why you have shorter wavelength here. Okay, because everything is electromagnetic wave, right? The shorter the wavelength, the higher the frequency, right? Yeah, that's the case. And finally, the electron should stay in attachment to the atomic model, but it's not the case. Okay, according to classical electrodynamic theory, okay, we will stop somewhere here. According to a classical electrodynamic theory, the frequency of the emitted EM electromagnetic wave should equal the frequency of the revolution of the electrons in their orbits. All right. As the electrons radiated energy, their angular velocity would change continuously, like in this figure, and they would emit a continuous spectrum, a mixture of all frequency, not the light spectrum as actually observed here. The electron should, the atom should emit the energy like this with a continuous spectrum, okay, if the Rutherford model is correct. But it's not the case, okay. They get the strip bar frequency, right? Anyway, even Rutherford's model cannot give a good, cannot give us a good, reasonable explanation to this phenomenon. It's the word because Nienbo developed his atomic model based on Rutherford model. Okay, model used the Rutherford model. Nienbo used the Rutherford model in a better way. Okay, various phenomena, including electromagnetic radiation emitted by a heated object known as black body radiation, and the emission of electron by illuminated metal known as photoelectric effects. That's one, this one, okay. And the emission of sharp spectrum lines by gas atom in the, this one, okay. And yeah, emission of sharp spectral lines by gas atoms in an electric discharge tube could not be explained well by using the classical physics. So the physicists need to develop new theory, okay. In 1905, okay, Albert Einstein proposed the existence of discrete energy packet during the transmission of light. A photon, also known as a light quantum, okay, quantum means the quantity of energy, actually, is a minute energy packet of a tiny amount of energy packet of any electromagnetic wave, and it could be computed by E equal to HF, okay. When H is the Planck's constant, which is 6.6 times 10 raised to negative 34 Joule second, and F is the frequency of the emitted photon. Okay, and I think now it's time to leave the lecture, okay, because we arrive at the same point as M604, and see, let me check whether you will appear in several YouTube channel. Okay, where is that? Okay, นะครับวันนี้ก็คงจบไว้เพียงเท่านี้นะครับเพราะว่าถึงจุดเดียวกันกับห้อง605แล้วนะครับก็จบไว้เพียงแค่นี้ก็การบ้านก็คงยังไม่ต้องมีก็ได้นะเพราะว่ามันยังไม่มีโจทย์ใหม่มาทำนะครับยังไม่มีโจทย์ใหม่มาทำก็เดี๋ยวซ้ำกับการบ้านเดิมเนาะที่ให้ส่งเมื่อสัปดาห์ที่แล้วนะครับก็คงต้องลาไปก่อนครับสวัสดีครับบ๊ายบายครับ M605 ครับถ้ามีข้อสงสัยก็แ
จ้งได้เลยครับแต่ว่าไม่มีใครดูเลยครับใน YouTube ก็คงไม่น่ามีคนสงสัยครับบ๊ายบายครับสวัสดีครับ
4 all right yeah stop